Good evening, everyone. Welcome back to NPTEL live session for the week 5. And today we will continue discussing about the circular dichroism and the chirality regarding that optical rotation and all the other concepts. And at last, we will be solving the assignment problems. So we will wait for 5 more minutes for rest of the participants to join, and then we'll start with the session. Thank you. Okay, so now we can start the live session. Good evening, everyone. So last live session was all about talking about the light and matter interaction. We discussed chirality. We also discussed something about the optical rotation. What is LCP? What is RCP? So I'll just give a brief uh, concept just about it, like what we discussed last week. And today's lecture would be all about how do we come to circular dichroism, because that is the main topic of your course, circular dichroism and mass spec spectroscopy for chemists. So we will be touching this circular dichroism part today, and then we will be having certain assignment problems. Say for example, I have made few around 9 questions for you people. So these we will be solving at the end of the lecture. Firstly, we will see what are the concepts. So, okay. So before that, I will just give a brief. And if at any point of time you are feeling that you do not understand the concept or you have missed the other live sessions, you can just put a message in the chat box or you can unmute yourself. So we'll start with the concept that at last, in the last live session, we discussed about the light matter interaction. In this one, we talked about the transition moment integral, which was nothing but, in layman language, if I am having an electron in a ground state, this is a molecule where the electron is lying in the ground state, because as you know, when there is no energy being absorbed by the electron, it will prefer to be in a ground state because that is highly populated and also the energy is very less. So wherever the energy is very less, that system would be called as a stable. So it will prefer to be in the ground state. But as soon as when we are hitting it with certain light, there is h nu, and as you know that energy is quantized, where h is a Planck's constant, that is a constant value, and nu is the frequency of the radiation. So that frequency would be different, and depending upon up to what level, up to what energy level we want our electron to get excited, that much amount of energy we are giving. So at last, it would be going up to this stage. It could be upspin or downspin or anything. Say, for example, this is your excited state. So going from ground state to excited state, what kind of that transition, whether it would be, if I'm not audible, just let me know because there is an issue with the internet. Okay. So when it has to get excited from the ground state to the another energy level, it is called like whether this transition is allowed or not. So do we know that whether that particular transition to a certain level, certain energy level is allowed or not? That is what we measure from the transition moment integral. So this we have discussed last time. And regarding that, we also talked about, we were asking that whether, how do we measure the chirality of a molecule? So we said if we put into a plane polarized light, so the chiral molecule will let this light or this plane to either rotate to the right side or to the left side. So right direction or left optical rotation. So the term came that was called optical rotation. So with this particular terminology, we can quantify that with how much amount it can rotate your plane polarized light. Now the question is why we are talking about the plane polarized light. Why not the white light? Because as we said, that white light is a combination of whatever the light we got from the sun. That is a combination of all the light in all possible directions. For example, it will go from here to here, this direction to this direction. Any direction is possible. So that can't be called as a monochromatic source of light. That is not having a single direction or something, right? So when we are talking with a plane polarized light, that is defined in particular plane, that is defined in particular direction. Now, why are we choosing this direction? Only a chiral molecule or its chirality can be defined when we have an environment which is chiral in nature. If we are putting a molecule, even though it is having an inherent property of chirality, and if you are putting it into an achiral environment, it won't be able to depict or show any property. For example, if you are putting a white light, which is having the light in all the directions, the chiral molecule also will not be showing any direction, any rotation, because say for example, if I have put it into the white light and the one half is going to the right side, one is left side, one is above, one is down, whatever the rotation is happening, that is cancelling each other. So we won't be able to see any kind of effect. So whereas in case of the plane polarized light, if I have a molecule, so this is my plane polarized light, and here is my, say for example, a chiral molecule. So this solution I'm taking, that is a chiral molecule. So you might have done the experiment of finding out the optical rotation of the sucrose solution, or might have read about it. So say for example, if I'm taking a sucrose solution and I don't know whether it is chiral or not. So I made it to pass, I made that light to pass through that solution. And what we found that it certainly rotated to it from its original position. This dotted one was its original position of the plane polarized light. Now it has been rotated by an angle of phi. So that phi we can quantify, right? This phi is nothing but your optical rotation angle, and that we can quantify. So from there we got to know, okay, sucrose solution is chiral in nature. So this is one way we can identify the chirality of our molecule. So that we read last time. So the question is why we are saying that plane polarized is light is chiral. We understood that it is going in one particular direction, but why it is chiral? So what we found that it is actually a superposition of two parts. One is RCP, which is nothing but right circularly polarized line, and LCP, which is left circular polarized line. By this, what we mean? Say, for example, I have the plane polarized light. If it is in this direction, I'm making it in more visible form. So if it moves like this way, if it goes like this way, now it is exactly at the middle, but to the totally right. Now it is somewhat here, and the last one, it is opposite. It can also be possible that it is going to the left side. This is what we were talking about, the right side. The light is having a direction towards the right side. It is not going towards the left side because it would be going in a particular direction. Now, what if it is going to the left side? So it is first point would be like in a straight way. Then the second would be going in a left direction. Then completely to the left direction, but in the middle. Then after that, it is slightly bent like this way. And ultimately, it is like this way. Now, when we combine, I will just highlight with a different color. So this is A, B, C, D, and E. And for the left one, these are same. So I would say F, G, H, and I. So when I am having, this is A only. So now superposition is nothing but the integration of both the parts. So when I will be having first part and second part, I'm adding both of them. The resultant direction would be your final plane polarized light direction. So ultimately we will be having one over the other. So this was the first A plus A. Then the second one is, you can see one is going here, other is going this direction. So the resultant would be lying somewhat in between. So ultimately, if I'll start with this one, it will go this. When one is this direction, other is this direction, both are having same distance, but they are opposite direction. So they will nullify each other. And ultimately, we are having like this one. That's why the whole plane polarized light becomes with the two arrows. Both the parts of right side and the left side, it is inculcating in between. And that's why it is made up of right side polarized light and the left direction polarized light. So this is right one, this is left one. And as you can see, these right and the left ones, they are giving you a helical kind of structure. Whenever there is a helicity, helical kind of structure is coming, that creates a chirality. Why so? Because if this is your right, and we know that chirality is something when we have two isomers, mirror images, they will not superimpose with each other. And this is right side, this is your left. And if I'll put a mirror in between them, so these two will become your mirror images just as your right and left hand. And if you'll try to superimpose each other, they will not superimpose. So that's why they are called as chiral. And this answers our question that plane polarized light, which is a superposition of RCP and LCP. I won't be repeating the full form of the RCP and LCP. We understood that it is left hand circular polarized light. RCP is right hand circular polarized light. It has nothing to do with any measurement or the distance. It is only about the direction. And they are creating a helicity, which is creating a chirality in that particular light. So is that clear, like why we are talking about a plane polarized light being chiral in nature? Is there any question?
Ma'am, plane polarized light, already we know that is in a single direction.
Yeah.
Helicity means, ma'am?
Helicity is, you can see this kind of a helical structure where it is moving forward, but it is having a circular motion. Say, for example, if you know
Oh,
that our electron or the waveform that goes like crust to trough this way, right? So this is having a helical motion. It is not going just a straight direction. It has to linearly move also, and it has to rotate also. Because as you can see, this is a kind of clock. It is going from this direction. So this way it is moving towards also, but it is having a circular motion. That's why it is having the helicity in it.
okay, ma'am, okay.
So is there any question? You're right that plane polarized light means it's just a single light, but we're talking about the direction. Direction doesn't mean that, okay, when I'm saying one direction could be either towards, I'm going straight, but straight could be like this, the straight also, back straight also. You understood? Like I can go to right side also, I can go to left side also. I'm not moving to right and then diagonally, not like this way. I have a direction. Either my straight could be right straight or it could be left straight. So you're understanding, like even if plane polarized light, we are calling it as a monochromatic. That means one frequency light is there. It is not having a combination. When we talk about white light, it is not having all the frequencies. Like say, for example, if I'm taking a wave number of 400 nanometer light and then 500, then 600, or among all of them, they would be having only one frequency. It is the only matter of like which direction it is going, which motion it is taking, whether it is going to the right side or it is going to the left side. That whole makes it a plane polarized light, because if I'm talking about a plane, it can't be a single direction only. So when I'm talking about monochromatic source of light, that means like it is only having one frequency, but that plane polarized light also comprises of right side and the left side, that both the motions would be there. Is that clear?
Clear, ma'am.
Okay. So this was the one case, that this was just the brief concept, like what we understood last time. Because when our main topic is circular dichroism, that is coming from your light matter interaction, that is coming from chirality. So if you remember that in the week one, we started with the symmetry of the molecule. We understood the concept of chirality differently. So say, for example, we got to know that how do we define the symmetry of the molecule, by defining its point groups and finding out the order or something like that. Then we came to the chirality concept, and we came with the conclusion that whatever the molecules, after understanding the symmetry, whatever the molecules, we can group them into C and DN point groups, and they should not be having any SN improper axis of rotation. So by this time, we were understanding that symmetry is clear. From symmetry, chirality we understood. Now, how do we detect the chirality of a molecule? For that matter, we talked about a plane polarized light. Why is it so? Because ultimately, it is just the interaction of the light and the matter. Matter is your molecule, and light is the source of this plane polarized light, which is having a certain frequency. That's why we are connecting the dots: symmetry, chirality, plane polarized light. Now, plane polarized light is chiral. So if my molecule is chiral, it would definitely affect the plane polarized light, either its optical rotation or any other concept that we are going to read about. So from the plane polarized light, we got to know that, okay, it's a combination of RCP plus LCP. That means it's a chiral. Now, last time we talked about, what if see the refractive index of RCP is not equals to LCP. Refractive index is nothing but your ratios of the speed of light in vacuum divided by speed of light in your medium. So this means when I have a solution, now this is my this is a beaker containing my chiral molecule. I understood by that concept, like, okay, I need to know whether the molecule A, which is dissolved in a certain solvent, it is having certain concentration. Now I've dissolved it in a solution solvent, and now I have a beaker which is containing my chiral molecule. I know that it is a chiral molecule. If you do not know, how you will get it to know? So what happens when I'm passing the light that is coming from the vacuum or the air, and it is going through a different medium that is passing through this medium. So this medium would be having different density. This would be having different speed of light. That can't be same which we are seeing in the air or in the vacuum. So it varies. So what if the RCP, that plane polarized light, which is going to pass through this, the one part is having more speed compared to the other part? They both are not equal. For example, they both are not equal. Generally, when we are taking a chiral molecule, one of the two parts would be interacting much faster compared to the other one. It is the inherent property of your molecule. That's why it interacts with one part, the one polarized part more compared to the other one. So the refractive index, the N value, it varies. So what we generally expect, okay, this is my plane polarized light, which is going through this solution, which I know that it is chiral, but you do not know. And later on, the ideal thing would be if it is at all not chiral at all. So the plane polarized won't be getting affected, because as I said, chirality will only be judged when there is a chiral environment. So if this molecule is achiral, and even if I'm giving a chiral environment, it is not going to affect the plane polarized at all. So the expected, there won't be any change. You can't see any change. That would be as such. But if it is chiral, and a chiral molecule has been given a chiral environment, now it will interact. Now it will behave whatever the way it wants to. So either what it does, either it will rotate the plane polarized light to right direction. So this was my ideal case. And now, as you can see, this was my ideal case, and it has moved by this much angle. Say, for example, this phi angle, or it moved by this angle. Sorry for the drawing. Same angle, but to the left side. So either it rotated my single, that straight line at the center, towards the right or towards the left. That is what we call as optical rotation. And this is what we understood, or we read about it in the last week. So is that clear, that why our plane polarized light goes to positive, or the goes towards the right side or towards the left side? That's why we say that a chiral molecule definitely rotates the plane polarized light either in the right direction or the left direction. That is a sign of chirality in a particular molecule. So is that clear?
Clear, ma'am.
Okay. So this we understood in the last live session also, and there were so many formula where we got to know that, okay, phi optical rotation is dependent upon the difference between the refractive index of both LCP and RCP. That L and R is nothing but the notation of LCP and RCP, and the full formula is 180 into the path length L into the difference of NL minus NR divided by the wavelength that the light particular, because when we are talking about a monochromatic source of light, it would be having single energy, single frequency, single wavelength, because we know that how the energy is related with the wavelength and the frequency. So all would be single. So this value is fixed. This value is fixed. Only this particular difference, depending upon different molecules, the phi value would be different. And depending upon that, it would be having positive sign or the negative sign. So this was the first case, that how the plane polarized light is going to react with our chiral system or any molecule system if we are expecting it to be chiral. So the second point could be, what if my refractive index of RCP is equals to LCP? That means the speed of light is same. They are moving with the same speed, but their absorbance are different. So their absorbance are different. That means they have, as we already talked about earlier, that if I have a solution and if I'm giving a light with I naught, there would be certain amount that it will absorb and certain amount it will transmit. So the absorbance value will become as a ratio of your log of I naught by I. So this we read it in the last to last live session. Okay. The similar way, if I am giving a plain polarized light and it is having both the components RCP and LCP, what if the absorbance of RCP and LCP is not same? One of the two would be absorbed more by the molecule and other remains as such. And this could be more clarified. So if this is my right side, and if it is moving like this way, so this is when it is passing through the molecule, but it is not getting absorbed. The RCP is not getting absorbed, but your left side. So if it is getting absorbed, so then amount would be less, even though the direction or the speed is same. Okay, the different. So here it would be like this way, this direction, then this, and then this. So now you can see that because LCP, that right side, the left side part has been absorbed more by the molecule because of its inherent property. That amount, as you can show, because this is a figure that with the help of which we can make ourselves understand how the absorbance and the variation of the speed of light is different. If I'm talking about the speed of light, the circle would be approximately same because absorbance is not happening. It's just the speed, like with what amount of speed it is going and coming back. But in case of the absorbance, we are showing with a smaller circle where it is shown that okay, some part has been absorbed of it. So when absorbance is different, so what will happen? Now, earlier it was a circular motion. It was expected when the absorbance has not happened, but now it will come like an ellipse form because it is no longer a similar part, like it is not going in a circular motion anymore. So because of this right side LCP and RCP and some absorption is happening, other than the circular motion, it is now showing the elliptical motion. So what happens? This becomes your AL plus AR. That means both the parts when they superimposed with each other, and this part becomes your AL minus AR. So wherever it is on the right side, as you can see over here. So this becomes your minor axis. And this becomes your major axis. And this is actually an ellipse. So because of, yes.
Ma'am, here AL means?
AL is your absorbance of that LCP, that left circularly polarized light.
Left circularly polarized light absorbance.
Yeah.
Okay,
because we are considering the condition where LCP has been absorbed and not the RCP. So that is just the hypothetical situation. You can take the reverse also. So depending upon that, your signs and that values will be different. Okay.
Okay, ma'am.
So now we got to know from the circular motion, it is going to an ellipse motion. So earlier what we saw, the first condition was when the speeds are not same, that speed of LCP is not equals to RCP. That means we talk about the refractive index, LCP is not equals to RCP. It arises the optical rotation, that phi. And the phi value depends upon NL minus NR. That is, sign convention is with respect to the whatever the convenience and whatever it is already there in the literature. And the second concept, if the speed remains the same, but absorbance happens, and absorbance of left circularly polarized is not equals to your right side, it will arise ellipticity. That means from the circular motion out, it is going to an elliptical motion. And the sign of ellipticity is given by this psi, and it is dependent on AL minus AR. So this is my ellipse. And you know that ellipse is having a major axis. This major axis is nothing, if you will remember, that this was my right side circularly polarized light, and because of this small portion of my LCP, when it comes back from the left rotation, it comes back. So you can see that it is adding on to this one, just an addition. So it becomes AL plus AR. Whereas in case of this one, when right side is this direction and left side is coming like very small in this direction, so it becomes an AL minus AR. So why A? Because even if you see the sign, the absorbance of left is more compared to the R. So do not get confused with the signs and the notations that we are giving. You're understanding my point? L is getting more absorbed, that's why its value is less. So when we are subtracting something, it has to be the absorbance value of L would be X, which is greater than the Y. This is the absorbance of AR, that R, and this is of L. So X is greater than Y. So L has to subtract the R value. Is that clear? And this is your minor axis.
Clear, ma'am.
Okay. So when we know that this is a situation, and if you will see over here, this angle is your phi, that ellipticity that we are talking about. And as we know that tan theta, I'm just considering any angle, tan theta is equals to perpendicular divided by base. That formula comes from your trigonometry. So perpendicular upon your base, and this one is your perpendicular, which is being drawn over here. So minor axis is your perpendicular, and base is nothing but your major axis. So if somebody asks you to find out the tan psi of that ellipse, then it would become perpendicular divided by base, which is nothing but your AL minus AR, which was the minor axis, upon AL plus AR. And if we just want the psi, the whole formula is 2.303. It is dependent upon AL minus AR, 180 degrees divided by 4 pi. Okay, so the meeting will be ending up in 10 minutes. So you have to rejoin the same link. So this way we calculated the ellipticity. The way we had phi depending upon the refractive index, this is psi depending upon the absorbance of your LCP and RCP. And this is the formula that we have to use. So is that clear? That how the plane polarized light interacts with your molecule, if it is at all the chiral, and how we can quantify, because we understood that, okay, we can see the direction, but the direction of your rotation or the ellipticity one value, only when the value is there, we can quantify how much it is chiral, which direction it is going, which direction it is not going. So these all the values are important for your quantification of the chirality of your molecule. So is that clear? Then we can move ahead.
Clear, ma'am.
Okay. So now the next concept is, as we already know that absorbance, because we were talking about the ellipticity, so absorbance E is nothing but your epsilon C into L, where E is your molar extension coefficient. This will tell you about the how much amount or what is the capacity of your molecule to let that light to get absorbed, and this is the molecular property. This varies depending upon one molecule to other. C is the concentration of your molecule, which can be fixed. And L is the path length through which the light is actually passing through your molecule. So if you see, these two both can be constant for a particular molecule, but epsilon value or two molecules. Say, for example, I've taken solution A and solution B, and I'm keeping concentration constant and length of the light also constant. So what is the factor that is actually going to change? That is only but your molar extension coefficient, which would be different for your molecule. Even if you try, it won't come exactly similar for all the compounds. So therefore, absorbance mainly depends upon your molar extension coefficient. And depending upon this, the psi can be known as, this one symbol is known as molar ellipticity, where it is given as 100 into psi divided by C into L. So for a particular concentration and length, what is your particular molar ellipticity corresponding to the molar extension coefficient? So this is the value, and this is also being given as, there is a certain, if concentration is known and L is known, which is standard values, we get 3300 into delta E. Delta E is nothing but the epsilon difference of right side to the left side. So these are certain formulae which could be useful to get the information about certain certain molecules. So up till now, we understood the concept. Okay, plane polarized light is chiral. It is chiral in nature. Then we understood if there is a difference between a refractive index, it will give you the optical rotation. Then we got to know if at all NL is equals to NR, that means speed of light in that particular medium is same, but the absorbance is not same, then it will give you the ellipticity. And also to add on to this particular point, if I'm talking about optical rotation, that phenomena comes under circular birefringence. Sometimes these kind of questions also being asked directly. And if it is ellipticity, it is giving rise to circular dichroism. So this is from where actually the topic, the name of the course starts, circular dichroism. Circular is nothing but that circular motion, you already saw that it is going in that particular direction. Di means two and chroism means two kinds of absorbance. So when the plane polarized light itself is giving two kinds of absorbance, one part is getting absorbed more, other is less. So that will arise ellipticity, and because of that, the phenomena is known as circular dichroism. Is there any question till now?
Ma'am, circular birefringence, once again explain, ma'am.
Yeah, so circular birefringence, we saw that how do we quantify our molecule, like whether it is chiral or not, even if it is not getting absorbed. So if you might have done that sucrose experiment in your graduation, or if you are in graduation, you might be doing. So if I'm taking a sucrose solution, so we know that sucrose is nothing but a carbohydrate, right? So we name it as a chiral. But what happens when I am putting it into a sodium D-lamp? So this sodium D-lamp is giving it a particular, say for example, 500 nanometer light. So this light is fixed. The monochromatic source of light is coming and it is hitting on this particular solution which is containing the sucrose. So what we saw, we didn't see any change in the absorbance. No color change, no UV, nothing at all, no change. But what happens? So if this light is coming like this particular direction, it actually rotates it in positive direction, that right side, or it is giving the negative value of 5, that means the left side. So the rotation happens when it passes through the super solution, and this gives us an idea, okay, this is having an optical rotation. That means our super solution is chiral in nature. And this phenomena going from, if this is my plane, this is a static position. If it is either going to the right or to the left, that arises because of the birefringence. That meaning of rotation from its particular position, that is called as a birefringence. That's why the change in the speed of light is giving optical rotation, and that creates a phenomenon of circular birefringence. The motion is still circular, and that is giving you left or right side rotation, that is called as the refringence. Similarly, if a molecule which is having a capacity to absorb the light, so if it is absorbing the light, the change in the color or change in the absorbance can be seen. This happens because of the molecule is chiral, and it is actually taking up some part of the light. It is taking or absorbing some part, either right side or the left side more, and it is giving a change in absorbance. So that will create a circular dichroism, because there would be di means two and chroism means two kinds of absorbance. So refringence is two types of rotations could be possible, and chroism means two types of absorbance are happening. So is that clear? Refringence, you can just remember the fact of refractive index. If the refractive index is different, that means speed of that particular part is more or less than the other part. So they are giving birefringence. Two refringes are there. And if there is two types of absorbances, that will give you dichroism. So now the terminology is clear?
Clear, ma'am.
Okay. So after 2 minutes, it will again start this live session. Then we will talk about what is required for a molecule. What are the main criteria? We understood about the plane polarized light, how it is chiral or not. What two phenomena are there when molecule is chiral and then it is going to give a different two quantification, whether one is phi and other is psi. But how do we detect our molecule is chiral or not, and how it is going to affect? So actually what happens is, for the absorption purpose also, or the optical rotation also, as we were discussing, that this is my excited state and this is the ground state, and this is an electron which we are talking about, and the light is coming, hitting onto it, and it is absorbing and it is going to the excited state. So actually the transitions or the absorption or whatever the dipole moment, if we will talk about the dipole moment, how it originates and how much in what classification we can have it. So what are the factors or how it can be affected? So this dipole moment, it is actually comprises of three parts: electrical dipole moment, magnetic dipole moment, or electric quadrupole moment. So what it means, if I'm just considering the charge and distance, I'm not considering the circular motion or the magnetic strength of it. So that will give you an electrical dipole moment, because say for example, two charges are there. One is minus C, one is plus C. The magnitude remains the same. It is only the sign that is changing. That charge sign is changing. And both of them, they are having an r distance. So